Imagine that our null hypothesis is that the mean blood pressure for all Americans is equal to 100. And our alternative hypothesis is that the mean blood pressure is not equal to 100 for all Americans. Maybe more, maybe less, or something like that. Okay. If I were to assume that the null hypothesis is true, that it's really all the average blood pressure for all Americans is equal to 100, well, if I took a sample from this population, right? Well, let's see, sample, I'm going to take a sample size equal to 100. Let's say that sample tells me that the standard deviation for those 100 people, or for my estimate for the population, is equal to 10. In other words, it varies, with a standard deviation of 10 above and below. And that since I have a sample size of 100, if I took repeated samples from my population, which has a mean of 100, what would I expect to see? What I would expect to see is, if I plotted all that distribution of all those means, is that the mean of all of those distributions, just like the mean of the population, is going to be 100. And I would expect to see the standard error, standard deviation of all those samples, is going to be equal to, 10 over the square root of the sample size, which is 100, going to be equal to 1. Okay, so I would expect 95% of the time, if I took a sample from this population, I would expect 95% of the time that the result, the mean for that sample of 100 people, would be between 98 and 102. Can we all agree on that? Yep. Okay. If I really want to be more precise, I would have said 1.96 times 1, or 98.104, 98.04 or something like that. But I'm not too worried about that. I'm just going to let it go with this. Okay. So now that would happen if this were true. Well, now I'm trying to demonstrate that maybe this isn't true. Okay. So now let's say that the actual average that we don't know, we're just guessing at it. Let's say the real average is 103. Right? The true mean is 103. Okay, what would that have looked like if I took a sample size of 100 and the standard deviation was the same? I didn't change the standard deviation. Well, what that would look like is the mean would be 103, pretty sloppy. Mean would be 103, right? But the range for 95% of the results from repeated samples of size 100 would be 101 to 104. Right? So if this is true, and as it happens that it's really equal to 103, if this is true, 95% of the time I would get a mean between 101 and 104 for whatever sample I took. What's that? 105, yes. Sorry. Okay. On Mondays it's 105. Okay, so at any rate, so that's what I would get if this were really this number. Now, problem here is that if this is true, I want to be able to say that this is false, reject the null hypothesis, and accept the alternative hypothesis, right? So if this is true, if this happens to be the truth rather than this, which is what I want, I really want this to be the truth, that means that a lot of the time I would get a value less than 102 when I took my sample from that alternative population. What percentage of the time would I get a result less than 102? How would we figure that out? Well, we know the standard error is 1, right? So 103 minus 102, 102 minus 103 is negative 1 over the standard error is 1. What's the z-score here? It's negative 1. So what is the area here? What percentage of the time would I fail to reject the null hypothesis? Because this, I would get a value, even though this is really what the population looks like. What percentage of the time would I fail to reject the null hypothesis when I really should? Right? Isn't that really what's going on here? Right? If this is really what the population looks like, and this is what my null hypothesis says that it is. Well, I want to know what percentage of the time would I get a high enough value for my mean that I would say, if we're above 102, below 98, I would say reject the null hypothesis, because there's less than 5% chance that it would be true. I don't know what that thing is. Oh, I guess that's some sort of, it's doing it again. Let me see if I can click those and make them go away. I can move them.
Tom?
Yes.
Do you have a time for like a stupid question?
Of course.
Again, just to go quickly again, that -1 that you got it again.
Yeah, what I'm looking at here is, if this is true, if this is really what the population is like, let's make sure if this is true, this is really what the population distribution is, or the sample distribution is, because the mean is really 103 in the population, not 100. Well, what percentage of the time would I get a value that's below 102? Why 102? Well, I'm interested in 102 because if I get a value below 102, I can't say my initial assumption is not true. I can't reject my null hypothesis. I need a value above 102 for my sample mean, or below 98, so that I can say with less than 5% chance of being wrong, alpha's 5%, alpha equals 0.05, that I can reject the null hypothesis. So if this is true, then occasionally I will get values less than 102. How often will that happen? That's going to happen whatever this area is, that percentage of the time. So what is that area? I can look that up in the z-chart. Anybody want to look that up for me? The area to the left of a z-score of -1? What? 0.1. I'm going to call it 16%. There's a 16% chance that I will fail to reject the null hypothesis when indeed the mean of the population is different than what I said in my null hypothesis is, right? You know what that thing's called? That's called your beta error, right? That's the percentage of the time that you will fail to reject the null hypothesis when you should have, because the real population mean is 103. Okay, how about this area over here? This whole area that's 84%, 0.84. 84% of the time, I will get a high enough value when I take my sample of 100 to say it's greater than 102 and reject the null hypothesis. That's called my power. Okay, so what would make my power better? Well, if the population were really 104, then it would be pushed over to the right, and 100 and it'd be 104 minus 2 be 92. So the chances I wouldn't be able to reject the null hypothesis are going to be less than 5%, and my power would be 95%. But I can't I can't alter what the real world is. I can't alter the real mean of the population. What's another way that I can make it so that these two distributions don't overlap so much? I can't really change my starting point, and I can't really change what the real mean is. What can I do to make them not overlap so much? Well, how about if these were, instead of looking like this, as if they each were narrower, right? What could I do that would make them narrower? Make the sample size bigger. If I make the sample size bigger, like if the sample size were let's see, let's see, 50 square, 50. What sample size can I use? It's going to give me a nice round number. That's 1, 200. What's going to give me 20, 400. Let's make the sample size 400, right? If I make the sample size 400, right, then my standard error is equal to 0.5. That's 10 over 20 is 0.5. My standard error is equal to 0.5. So my normal distribution, if the null hypothesis is true, right, my 2 standard deviations to the left, 2 standard deviations to the right is going to be 99 to 101, right? It's going to be narrower. All I have to do is prove that the real distribution is bigger than 101, not 102, because of the sample size, or smaller than 99. Well, if I assume again that my population is 103, I'll go back to 103, right? My real true population, which H all, the alternative hypothesis is true, and it's 103. And we may have to make this assumption in order to do this calculation. If I assume it's 103, well, two standard deviations below that is going to be 102, and 2 standard deviations above that is going to be 104. This time it's 104, right? Maybe I was thinking ahead. Maybe I just don't know what I'm doing here. So let's take a look at this. Well, they really almost don't overlap at all now, do they? Right? So 101 is going to be way down here, well below the 5% chance of failing to reject the null hypothesis. So my beta error is very, very tiny, and my power, the probability that I'll reject the null hypothesis because it needs to be rejected, is very large. Okay. So shall we do one more of those? Yes.
So, when we said that the alternative hypothesis was that sample mean was actually 103, not 100.
Yes.
I calculated that the probability of being less than 102 is 0.06. I mean,
0.16, yes.
That is the probability that you would fail to reject the null hypothesis.
Exactly right. Even though the real population is 103. That's called beta error, right? When you reject the null hypothesis and you shouldn't, that's called an alpha error. When you should reject the null hypothesis and you don't, that's called a beta error. Okay? And 1 minus the beta error, in other words, the probability that you'll get it right and reject the null hypothesis, is the power. Okay, and we want power to be high. We want to make sure that we get a sample size that's big enough that it's really likely that we're going to reject the null hypothesis if it needs to be rejected. Yes.
So is the beta error here 2.5%?
The beta error here is probably even less than that, but yeah, it's 2.5% or less. It got so nasty I can't see anymore. So let's do one more, okay? Okay. How are you guys doing online? Increase. Oh, good. Thank you, Emily. Increase the sample size. We got a couple of people that are pretty sharp online too. Okay. Okay, I'll make up a new example. Okay, we're measuring blood lead levels in children. My null hypothesis is that the mean blood lead level, okay, PB, I guess, is equal to 0.05, right? I won't. Let me use round numbers. Is equal to 5 micrograms per deciliter. Micrograms per deciliter. My alternative hypothesis is that it's not equal to 5 micrograms per deciliter. Okay, I'm not going to deal with one-sided or two-sided tests because I think that's going to get us a little bit more confused. So I'm just going to let that drift for now. Let's say that this is a study where we want to prove that a particular population of children is blood poisoned. That, I'm going to, matter of fact, make it a little bit more realistic. I think the current action level for lead in children is 10 micrograms per deciliter, I believe. Okay, so I'm going to make both of these 10. So I want to prove that with 95% certainty, less than 5% chance of being wrong, that the current, that this population of children, whichever population they are, is significantly is over the average blood lead level is over 10 micrograms per deciliter. Okay, so now if I assume that the average is 10, right? That it's 10, and I took a sample size of I'm going to take a sample size of 36. And the standard deviation is equal to, let's say 3. Okay, what's my standard error for a sample size of 36? Is 36, 3 divided by square root of 36, which is 6, is going to be 0.5. Okay, so if I look at this population here, my null hypothesis, if that's true, let's assume for a moment that that's true. This time I'm going to plot them on the same plot. Let's assume that that's true. Okay, my mean would be 10. And if I took repeated samples, it would be a normal distribution, right? And what would be the range for 95% of the results? It would be 9 to 11. Everybody agree with that? The standard error is 1/2, so 2 standard errors to the left and 2 standard errors to the right would be 1 for in each direction. Okay, so that's where I would expect 95% of the results. So that means that if I go to another population, or if I go and sample this other population, which I'm saying is my alternative population, which maybe this is not the true population, maybe this is a true population. If I look at this other population, take a sample of 36, right? Well, how high a number would I have to get for that average in order for me to say with less than 5% chance of being wrong that it's not 10, it's different than 10? I would have to be above 11 or below 9, right? When I took a sample of this new population, of this other population, theoretical other population, right? Because if it's not above 11, that could happen here. That's within my 95% chance of occurring, right? I need for that sample to be greater than 11 or less than 9 in order for me to reject the null hypothesis. Okay? Okay, raise your hand if you're at least a little comfortable with that. Okay, we don't need much more than a little right now. Okay, so now I'm going to look at, I think that this population really has a problem with high blood lead levels. I think this population actually has a blood lead level of 12, right? I think that mu average is equal to 12. Why am I taking that guess? I'm taking that guess because based on what I believe to be true, maybe other studies that have been done, maybe surveys, maybe just guesswork. Maybe I think if I can show 12, that it's really 12, that would be a significant enough difference for me to say that they have more than the average kid in this population is above the action level. Okay, so let's say that it's 12. So now in the distribution, let's say that the standard deviation is the same, right? Standard error is the same. The sample size is the same. The only thing that's changing is where my mean is. Well, what would this distribution look like? Well, this distribution would look just like this one, except the mean would be at 12 instead of 11. So if I took a sample from this alternative distribution, what would that look like? Well, let's see. I know that the 95% of the values are going to be between 11 and 13, right? So it's going to look something like this. 95% of the values are going to be between 11 and 13. So there is a bit of overlap here, right? But not as much as before, is it? So let's see. 11 is how many standard deviations below 12? 2 standard deviations. So the area in here is roughly how much? 2.5%. Good. So that means that if this is true, that the mean for this population is really 12, not 10, right? That means only 2.5% of the time would I get a result less than 11. And if I did get a result less than 11, I don't know this exists. if I did get a result less than 11, it would lead me to believe that I should not reject the null hypothesis. That would be a mistake. That would be a beta error. That area represents a beta error. You fail to reject, even though the mean of the true population is 12, not 10. What's my power in this situation? The power is the percentage of the time that I would reject, which is the rest of this curve, right? Which is how much? 97.90, right, 1 minus beta, or 97.5%. Okay?
So
That's pretty good.
5% is the beta error.
2.5%, yes. 0.025 is the beta error, right? So if let's say that instead of 11, I had said, instead of 12, I had said the other, like I think this population is actually 11. That wouldn't work very well for if it were 11, because if it were 11, the mean would be right at the point where we would reject the null hypothesis. That means half of the results would be below 11, even though it really is different than 10, it's 11. Half of the results would be under 11. So 50% of the time, we would fail to get a result bigger than 11, which would allow us to reject the null hypothesis. So our beta error there is 50%, and our power there is 50%. We don't want power like 50%, because what that means is that we're going to go through all the trouble of doing this study, and we only have a 50% chance of being able to reject the null hypothesis. We want something better than that. And one way to get something better than that is to increase the sample size. Now, there is a way using these graphs to calculate how you could calculate the sample size that you would need for a certain power. I'm not going to go over it now. We're going to move on for a little bit and come back. I'm going to post a link to this other guy with the really nice graphics on YouTube. It's like about 25, 30-minute YouTube session. That he also does this. He goes through this. Levi's gone through this. I've gone through this. When you look at him going through it, each time you see it, I think it'll make a little bit more sense, especially since we're each taking slightly different kind of routes to the same thing. Okay. Yes.
I'm sorry, can you explain again how did you get the beta error? How did you calculate that beta error was 2.5?
I calculated beta error was because if the mean of the population is really 12, right, and the standard error is 0.5, right? Well, if I look at this, 11, right, would be 2 standard deviations below the 12, right? So 95% of the results would be between 11 and 13. But I need a result that's bigger than 11 to reject the null hypothesis. And I'm going to get that, right? But there is a little bit of every once in a while, I am not going to get it. See, this 2.5% of the time, I'm going to get a mean when I take a sample of 36 people that's going to be under 11. So even though it's true that I should reject the null hypothesis because the mean is 12, not 10, right? The mean is not equal to 10, it's equal to 12. Even though that's true, 2.5% of the time, I'm going to get a result that's less than 11, which is not going to allow me to reject the null hypothesis because I'm not beyond that point where I have a less than a 5% chance of being wrong if I reject it. I'm not beyond that 2 standard deviation, 1.96 standard deviations below or above 100.
When you go back to that original, I think that's the way to think of it. When you have to look back. It's hard
Right.
to see it there, but you look back.
Yep, it's hard to see anything there, but yeah.
It's less than
That's the nature of the
less
beast
than
here. That's why his graphics, I think, will help because he has very neat kind of like professional graphics and stuff like that. He's not drawing it by hand. So it'll be easier to see rather than trying to look through my scribblings.
And it doesn't matter that, like, you don't have to account for that if it's less than 9 piece. Like,
Oh, that's a good question. Normally we're doing a, notice that this is a 2-sided test. Equal to or not equal to. I set it up as a 2-sided test, right? So you are kind of, like, remember I made an assumption about what the real population was. I said, you know, I'm doing this study because I want to prove that it's different. So I got to make an assumption, and the assumption I'm starting with is that it's going to be 12. So you got to choose. You got to choose a side, right? You got to choose whether you think it's going to be 7 or you think it's going to be 12. However, if I chose 8 instead of 12, same distance below the mean, I'd get the same result.
But in that case, you'd be looking at what's the probability of it being greater than 8.
Or yes, yeah, or less than 8. Yeah, less than 9 actually. What's the probability of being less than 9? Because in that case, I would reject the null hypothesis for any result that's less than 9. Right? So if I did, let's see, this is 10. If I did 8, right? Not 7, but 8. If I did 8, then I would still get 8, 9. Then actually, if 8 was the mean, if 8 was the mean, then this would still be 16%. Right? Because it would be actually 2.5%. It would still be 2.5% because this is 2 standard deviations different. Right. So you would get the same result. Okay. So yeah, a lot of times, in a sense, kind of, what you're doing is your null hypothesis, the distribution of your null hypothesis is usually two-sided, but the area that you're interested in for your beta is one-sided because you're only interested in the part that overlaps down here. Okay. But you have to pick, in other words, in order to calculate the power, you have to make a judgment as to what the mean that you're looking for is likely to be for the alternative population.
But I was just thinking, like, we say that the percentage of the time that it's less than 11
Yes.
is the percentage of the time that you would fail to reject the null hypothesis.
Correct. Yeah, because you need it to be. If you look at if you look at the distribution for the null hypothesis, we can't reject the null hypothesis unless the sample size, the sample mean, is greater than 11, because that's 2 standard deviations above the mean.
8 is also less than 11, but if it were 8,
Oh no! In that case, it's got to be less than. In other words, if the true population mean were 8, right? Where you're saying what you're saying there is that you could also reject the null hypothesis if the population, if the null hypothesis sample means were below 9, right? So you
but
could.
I wasn't saying if you were hypothesizing that the true mean were 8. I was just saying that isn't 8 included in that portion that's you're saying is less than.
Oh yeah, no, but if I'm looking at if I'm making the assumption that the true population mean is 8 instead of 12, right? Then I'm looking at a different distribution down here, right? You know, and that distribution it has the same amount of overlap as before.
Yeah, I get that part. I was just saying if you're still going off the assumption that it's 12.
No, I'm not. I got to choose one or the other.
Right.
I have to choose either
12.
8 or 12. If I choose 12, right, then I have a 2.5% chance of failing to reject the null hypothesis, right? Because 2.5% of the time, I would get a result, given this standard error, 2.5% of the time, I would get a result that would be less than 11.
But it's not just that it's less than 11. That's what I'm getting tripped up about.
I'm sorry.
What I'm saying is, like, how come numbers like 8 aren't included in that 2.5%? Like, couldn't you get an 8? But why would you then? But then you would reject.
Oh no! What are the chances if the real population is 12, and like there's only 2.5% of these possible samples are below 12? What are the chances of getting something that's as far down as 8? That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 standard deviations away. The chances of that are like, chances like an asteroid hitting tomorrow.
Okay.
It's infinitely small. Right? So I'm only interested in how much of this tail overhangs the point at which I can reject my null hypothesis. Okay. The only reason I would say 8 is you might say, remember this is a two-sided test. You might argue, oh, well, the population that I'm examining, I think they're less than 10. the average. So I'm going to use 8 because I think they're 8. And then you would just set up another distribution here, and it would overlap. It would overlap the same amount, 2.5%, except this time it would overlap 9 by 2.5%. Like I said, you guys will get another shot at it. Let me make sure nobody at home is falling asleep. Okay, you guys are still around at home, right? You can still see me, still working? Good, okay, great. Right, like I said, first time, I think there's about, I'm going to give you I'm going to do a distribution now. First time, I think that there's 3 standard deviations to the left chance that you're going to understand this stuff. By the second time, I think you're up to about 16%. By the third time, I think you might be getting across 50%. Right? But as you watch the video, as you go through back over this and stuff like that, it'll make sense as you do it over and over again. And as you set up your own examples, make up your own examples, and kind of like the way we did now, to see how these different distributions would overlap one another. Okay, so don't if you still got questions, don't worry about them. When you see the video, watch that video, and maybe that'll help out. Then maybe like later on in the week or something like that, maybe we can do some. Maybe I can post another example of my own. Okay, or maybe pull something from the book. There's probably an example I can pull from the book. Now, how would you decide on a sample size? What's the point of all this? Point of all this is that you want to make a judgment as to what your sample size has got to be, right? That's why you're interested in power. You're not really interested in power for the sake of calculating what the power is. You want to decide what your sample size has to be. So what does the power tell you? The power is the probability that you're going to be able to reject the null hypothesis, right? And publish your study. Okay, so now if you have a power of 50%, if you have a situation where that you want to show a difference between 10 and the population mean, like in this case 12, we think it's 12, right? A power of 50% is not so good because you got a 50-50 chance of not being able to accomplish your goal. Now, do you want a power of 99.9%? Yeah, it would be great, but what would that mean? That means that you're getting a sample size that's so big that you've added to the expense and the trouble of doing your study. So, depending on what your tolerance for failure basically is in rejecting the null hypothesis, maybe 80% is good enough for you. So you can, if you want, calculate a sample size that'll give you a power of 80%. Now, I'm not going to go into it, but basically, what you can do is you can say, like for instance, in this example, 11 is the point where we would reject the null hypothesis. And also 11 is the point at which we're looking at for what's the probability of that we wouldn't be able to, that we would fail to reject the null hypothesis. But you can figure out what the z-score is for what this value 11 is, and you can calculate how many standard deviations away from 100 this is, right? And how do you calculate that? Well, it's the z-score is equal to the distance between 100 and that value 11, 1, over the square root of the sample size, right? And now you can also figure out a z-score, a value of 11, and what the z-score would be for the other population, 102. So you can figure out z-scores for both of them. It's the same standard error, at least we're using the same standard error. So you'll know the two z's, you'll know the standard deviations for both of them, which are the same in this case. And then the only unknown that's left in these two equations is the sample size. So if you have these two equations, you can set them up so that you can solve for the sample size. Okay. However, a lot of people don't bother with that. A lot of people use a device, a formula, a quick way to estimate it based on the margin of error that you're willing to tolerate. It's in the book. I'm not going to go over it right now. I want to move on to that single sample t-test. But there is a formula in the book that uses the margin of error that you find that you would expect to calculate the let me see if I can't find it. Calculate the sample size that you want. Okay, can you see that? Maybe I can make that bigger. Okay, okay, there's your margin of errors times the Z is represented by the confidence interval that you want. ME is the margin of error, right? And sigma, you can solve for the square root of n given that you have acceptable margin of error. What's the margin of error? It's 1.96 times the standard error. Okay, so I'm not going to go through that right now. Okay, but there are a couple of examples in the book. But what I want to do is I want to quickly go make sure that we don't miss this idea of running some t-tests and so on. So let me see what I have here. Let me see. I uploaded a document to Blackboard, which is session 7C. Okay, if we look at session 7C, we have some examples. Okay, you guys, hopefully you guys online can find that as well. Okay, totally awake. Okay, the mean SAT score for the population of first year students at Hunter is 620. The standard deviation of scores in this population is 95. An investigator believes that the mean SAT score of first year psychology students is significantly different than the rest of the Hunter population. The mean of the sample of 36 randomly selected first year psychology majors is 648. The standard deviation for psychology majors is assumed to be the same as for the general population. Okay, so what do we know there? We know that the mean SAT score for every student at Hunter is 620. I'm going to make that red. Is 620. That's a fixed number. That's the population average, right? We know the population average. What he's speculating at is, they didn't separate in the database the SAT scores by major, right? So he needs to, he can't go and track down all the psych majors, but he needs to probably in Hunter, there's probably what, like 5,000 psych majors, maybe more, 10,000. He can't go track them all down. So he's going to take a random sample of 36 psych majors and find out what their mean SAT score is. Turns out sample size is 36, and the average for his sample is 648. Well, now he knows that the standard deviation for the general population, right, was 95. And he's going to assume that, there's no reason for me to think the variability is different, just the average is different. So he wants to know, can I prove that, in fact, psych majors have a different average than the general population at Hunter? Okay, so now let's take a look at how we would set this up. Okay, we like to do hypothesis testing, so we're going to write out our hypotheses. Okay, let me get rid of this thing. Because if I can't do this, I can get both of these on the screen at the same time. Okay, so what's my null hypothesis? What do you think my null hypothesis would be here? Right, they're the same. The mean for the general population is equal to the mean for psych majors, right? Which happens to be equal to 620, right? I don't really need that. I just want the two means to be the same, right? So now I could also just describe that as the mean for psych majors is 620, since that's the mean for the general population. That's a little bit neater, I think, right? I mean, you could have done it either way, but that's a little bit neater. Okay, so what's my alternative? That's my null hypothesis. What's my alternative hypothesis? That the mean for the psych students is not equal to 620. Nobody speculated about whether it's higher or lower. We just know it's different. Okay, so we want to do We want to test this hypothesis. Okay, so now, what's the sample size we took here? 95, right? Well, since the sample size is 95, oh, I'm sorry. Yeah, standard deviation is 95 of the population is 95. What's the sample size? 36. N is equal to 36. Okay, so what is my standard error going to be for a sample of size 36? It's going to be 95 over 6, which is, how much does that come out to? I'm sorry, how much? 15 point, I'm going to call it 15.8. I don't want you to round off until you're done, but I'm rounding off so we can get done sometime tonight. Okay, so that's my standard error, right? So now I have to figure out, well, what's the probability that I would get a value that's that different from 620? Okay, and how do I figure that out? Well, either the t or the z-score. Which one do I use here? I'm going to use the z-score. I have two reasons for me to use the z-score. One reason is that the sample size is bigger than 30. The other one is that I know the population standard deviation, right? Okay, so I had two reasons. So z is equal to, what is it equal to? It's equal to 650, what is it, 648 x minus the mean, 620, over the standard deviation, 15.8. Z is equal to 28 over 15.8. So what's the z-score?
1.7.
I'm going to change this. I don't like that. I'm going to make it 658. So this is 38. Now if it's 38, what's my z-score? I got a reason for doing this cheat. Okay, I'm going to,
38 divided by 2.
yep,
2.4.
2.4. Okay, so now what's the probability that I would get a z-score that these two would be that far apart in terms of the z-score? Well, if I go back to my normal distribution, what's the probability that we would get that extreme a z-score? In other words, our result, if the population, if psych majors really had a mean of 620, what's the probability that we would wind up with a result in this sample that far out? What is that p-value there? Right?
We have to go to the C chart.
You got to go to the chart, yes. So what is the z-score for negative 2.4 and positive 2.4? I mean, what is the area? 0.00, 0.008 on the bottom and 0.008 on top. Two-sided test, right? So I got to look at both sides. So the p-score is really the sum of those, being further away than minus 2.4 and further away than plus 2.4. So my p-value is 0.016. So my probability of having an outcome of 658 for this sample size, if the null hypothesis is true, is less than 2% chance of that happening. Okay, so now what level of error am I willing to tolerate in most of these studies? What's my alpha usually equal to?
0.005.
0.05, right? Whoops, 0.05. Is my probability of being incorrect if I reject the null hypothesis less than the level of tolerance I have for it, less than 0.05? Right, so what do I do with my null hypothesis?
You reject it.
I reject it. Everybody agree with me rejecting the null hypothesis? Right, because the mean I got from that sample was so far away that it's unlikely that it was really from this population. Okay, will I ever get a p-value of 0? No, this is asymptotic. I probably will never get absolutely 0. I might get 0.000, some ridiculously small number, but not necessarily 0, right? Especially on a practical basis, you wouldn't get 0. Okay, so now this is pretty nasty over here. I'm going to do this again, except this time my sample size is going to be equal to 25. And I'm going to say my sigma is, well, that's really my standard deviation is 95. I'm basing it on the sample that I took, the 25 people that I took. I don't know the population standard deviation. So let's set up our null hypothesis again this time. What's my null hypothesis? Well, why is that doing that? My null hypothesis is that the mean for psychology majors, right? Let me just check the time here. We got a little bit. Mean for psychology majors is equal to 620, right? What's my alternative hypothesis? Same thing. Mean for psychology is not equal to 120. That's 620. Okay, so now what's my standard error? My standard error is equal to, well, 95. Nothing's changed except that I'm doing this. I got that 95 from my sample of 25 people, not from the population, right? My standard error is 95 over the square root of the sample size, which is 5. So what's my standard error? Huh? How, 19? I'm sorry. 18 or 19? 19. Okay, 19. Okay, so now let's do this again. Let's calculate a z-score or a t-score this time. T-score, right? We got to calculate a t-score because we don't know the population standard deviation, right? We based it on our sample standard deviation, and it's a sample size less than 30. So t is equal to, well, let's see, we got to figure it out here. X minus mu over the standard error, which is equal to 658, just like before, minus 620, over 19 is 38 over 19. That's an interesting number. What did I get? T is equal to 2. If this were a z-score, would you reject the null hypothesis? Is it bigger or less than 1.96? It's bigger than 1.96, right? If this were a z-score, there'd be less than 2.5% chance of getting it at the high end, right? So you would reject your null hypothesis. But it isn't, it's a t-score. Let's go to the t-table and look up for a sample size of 25, how big a t-score we need to have less than 5% chance of being wrong if we reject the null hypothesis. I think I got it here. I got to go on to Blackboard to get mine. Oh, now maybe I have it here somewhere. I can probably just search for it. T-table. T-table, let's see. Come on. T-score. Come on. You see it there?
No, T-table is the name of the document.
The T-table? Is there a space?
T-dash table.
T-table. There we go. Good work. Thank you. Okay, so I'm going to blow this up. So let's see. For an alpha of 0.05, right, which is 2.5% in the lower tail, 2.5% in the upper tail, confidence interval 95%. For an alpha of 0.205, my degrees of freedom, sample size 25, so my degrees of freedom is 24. So the t-score that I have to exceed in order to reject the null hypothesis, if it had been z, 2 would have been great. But since it's a t-score and the sample size is only 25, 24 degrees of freedom, I need to exceed a t-score of 2.06 in order to reject the null hypothesis. So do I reject the null hypothesis here? No, I fail to reject it because I haven't exceeded the t-score that I need to have less than a 5% chance of being wrong if I reject the null hypothesis. And why did this happen to me? This happened to me because it's the same numbers that we used before. It happened to me because I didn't know the population standard deviation. I had to depend on the sample standard deviation. And that meant I had to use a t-test instead of the z-test, right? So that's what we do with a t-score. This is a single sample t-test. Now I just want to show you so that you're not always, in a situation where you have to do this manually. Let me see if I have this.
Hey, Tony,
Yes, sir.
you use that section, how did you, question T.025, how did you pick that one particularly?
Oh, well, it's the right tail is 0.025.
Okay.
That means the left tail is 0.025. So it adds up to 5%,
Okay.
right? The distribution is 5. Okay. So let me see if this opens up. So I'm opening a file up in SPSS. I hope it's one that I want. It's a little slow getting started. Let me just make sure you guys online are okay. Okay. Still bouncing. That's a good sign. Come on. It'll pop up. It'll come up suddenly. Let me see if I can't start it from here too. Oh, here we go. Okay. Okay. Oh, remember that example we were talking about last time? Number of slices of roast beef, right? That's the same example, right? We did that, I think, with Excel, most likely. Okay, so now I'm going to say my null hypothesis here is I'm going to take the average of this. I'm going to say analyze, descriptive statistics, explore, and when I go into descriptive statistics, I can say analyze, descriptive statistics, I can say frequencies. Frequencies you would use if you're doing counts. Like if you're looking at categorical variables like gender, and you want to know how many males and females were in the study, you would use frequencies for that. Descriptives gives you the basic descriptive statistics for one of your variables. I can use that right now, in fact. I clicked on descriptives, it gave me slices. I'm going to move that variable slices. Very often you'll have many variables, and so you have to choose which one you want to work with or which group you want to work with. I'm going to move that in there, let it know that's what I want to work with. It's going to calculate standard deviation, minimum, maximum, variance, range, and so on and so forth, and the mean. And I'm going to say, okay. It's going to do that calculation for me. And bingo, the mean number of slices in these, how many stores were there? 16 stores was 10 slices. The average number of slices of corned beef that you got on your sandwich, right? So now I go to California, right? Go to California, and California says that, hey, listen, I actually did this a little backwards. I want to compare California, which has 8 slices of pizza, 8 slices of corned beef on their corned beef sandwiches. I want to see if they're different than New York, if New York is statistically different. Well, I took a sample of size 16, and it looks like New York is different than California, which gives you 8 slices. But it's a sample. It's not every store, every place you can buy corned beef in New York. So can I reject the null hypothesis that the two of them are equal, and that indeed New York gives you a different amount than California does? Well, in order to do that, we have to do our t-test, right? Now, as it happens, our standard deviation from, I don't know what standard deviation is in New York. Standard deviation is 3.1 for the number of slices. And our sample size is 16. So our standard error would be 3.1 divided by 4, or about 3/4, right? So now I have to determine, is that enough of a difference, 8 versus 10, to be able to tell whether or not there is a difference in the number of slices you get in California and New York? Well, how would I set this up? I would say T is equal to 8 minus 10.06 over the standard error, which was 3/4. I would get it, that would give me my t-score, and then I would go to my t-table and look up for my critical value at t, what I need to exceed in order for me to reject the null hypothesis, right? So if I were to do that right now, let's see what I would get. I would get 8 minus 10 is 2, divided by 0.75 is roughly 0.75, I think, right? That look right? Yeah, a little bit more, 0.8. 2 divided by 0.8 would be 2.5. And I would go to my t-table, and my t-table would tell me that the critical value for t-table the critical value for that outcome for a sample size of, no, I missed it. Critical value for a sample size of 15 degrees of freedom is 2.13. 2.5 exceeds that. Yes?
So that 2.13 is not the T, it's not T, that's the critical value?
That's the critical value of T. T is 2.5. T for this study is 2.5, right? Because it's the difference 2 over the standard error. X minus is mu.
So we should call that.
We should call this the critical value. Okay. So this number is, if you got that T value, you have exactly 5% chance of being wrong if you reject the null hypothesis. Well, let me finish this up in SPSS. So I'm going to go into SPSS again, except this time I'm going to go to Analyze. I'm going to go to Compare Means. Isn't that what we're really doing when we do a Z-test or a T-test? We're comparing the mean of this group to the mean of that group. We can compare means of a one sample t-test. This is a one sample t-test because we only have one sample, the 16 stores in New York. We're comparing it to a number we know is true for California. That's a one sample t-test. Independent sample t-test is when we have two groups. If I go to California and sample 16 stores, I go to New York and sample 16 stores, I have two independent samples. And I got paired samples. If I go to each store, before and after, there's a price increase in the corned beef, and see whether or not the number of slices increased or decreased, I could use paired samples because I'm looking at the same store before and after. In our case, we're looking at a one sample t-test. We want to compare our average for the 16 stores to the number, what was the number again? 8, I think, 8 slices. Okay, so let's see, test variable is 8, is slices, and the test value is 8. And I'm going to click OK, and it's going to do our t-test and give us the result just the way we would have done it if we did it manually. So if we take a look at this, let's see what we get. We get degrees of freedom is 15. The t-score is 2.636. We said 2.5 because we rounded, but it's really, we would have calculated exactly the same thing. The significance is 0.019. That's two-tailed significance. In other words, that's the p-value. The probability of being wrong if we reject the null hypothesis is 0.019 because the t-score is so big. So not only did it tell us that since the chances of being wrong, the p-value is less than 0.05, it actually gave us the exact probability. When you use a t-table, you don't know what the probability of being wrong is. You only know it's more or less than 5%. Right? That's what that critical value of t. But you don't know if it's 4% or 3.5%. The SPSS actually gives you the exact value, just like you would get if you did a p-value and you were using the z-table. Okay, so this tells me, this significance, substitute the word p-value or probability of being wrong if you reject the null hypothesis for significance two-tailed, 0.019. And you don't have to worry about adding the left tail and the right tail because it's already doing it for both. See, it says two-tailed, right? So probability of being wrong is less than 2%. So we reject the null hypothesis, just like we did a moment ago when we did it by hand. Okay, so what's the t-test do? T-test takes your sample, compares it to another sample mean, compares it to a fixed value, and so on and so forth, and tells you whether or not those two values are far enough apart for you to say that those two population means are really different. Okay,